Okay, so for chapter 2, it starts very simply with what is an atom, right? So an atom, of course, is, you can think of an atom as the smallest unit of matter, right? So it's the smallest unit that has mass and takes up space, I believe, is the definition of an atom. And you guys need to know the subatomic particles, which of course would be protons, neutrons, electrons. You need to know which ones are charged, what their charges are. And again, I'll just go through that really quickly. Protons are positively charged, neutrons neutral, and electrons are negatively charged. You'll see the next item there, atomic number. That's something from the periodic table. Again, those of you that have more familiarity with chemistry, you'll you'll know where to find the atomic numbers. If I'm going to ask you to use the atomic number on a test, it'll be in the given portion of the question. Okay. The atomic number that's equal to the number of protons that a particular atom has. Right? And remember, atoms that share the same chemical properties form an element. Right? So for example, if atomic number, if we were talking about, I don't know, let's say oxygen, atomic number of oxygen is 8. It has 8 protons. Okay? The atomic mass, that is the protons plus the weight, the mass of the protons plus the mass of the neutrons. So in my example for oxygen, the atomic number is 8. The atomic mass is actually 16. That tells you the number of neutrons by subtracting the number of protons from the number of the atomic mass. That's how you procure the number of neutrons. Right? Protons carry a positive charge, electrons carry a negative charge, and when an atom is neutral, there will be the same number of protons as electrons. Okay? The electrons are arranged in energy shells around the nucleus of an atom. The nucleus of the atom, again, still sticking with oxygen, we would draw 8 protons and 8 neutrons here in the nucleus in the center. And then around that nucleus, that's where the electrons are. And the electrons, there are 2 that fit in the first shell, and then 8 that fit in the second shell. But since oxygen would have these 8 positive charges and 8 negative charges, 8 electrons when it's neutral, there would only be 6. I'm just drawing them as dashed lines in that second shell. But the second shell holds up to 8, and the third shell also holds up to 8, called them electron shells. The outer shell, of course, is the valence shell. That's where the chemistry is going to happen. And we aren't going to use any atoms that go further than that third energy shell. I put isotopes on there as just a definition that you need to know. An isotope is a form or an atom, a group of atoms of particular element that have a different number of neutrons than the majority of atoms in that element. Right? Probably the most familiar you might recognize would be carbon 14. Regular carbon is carbon 12. An isotope of carbon will be carbon 14. It has 2 extra neutrons, which is what makes it carbon 14. It changes its atomic mass. I put a list there of the atoms, the elements that are most commonly show up in living things. I think your textbook even shortens the list even more to like 3 or 4. If you take a look at that table in your book, I think you can see that we're primarily made of oxygen, nitrogen, hydrogen, and carbon, right? So you can like actually reduce that list to even fewer. I would expect you to be able to recognize the chemical symbols for those elements and know what they stand for. Again, you can look them up in your book. And the rest of this chapter is about how elements interact with each other to form chemical bonds. So we have 3 types of bonds to discuss: ionic, covalent, and hydrogen bonds. Your textbook puts covalent bonds first. I like to do ionic bonds first. So if you see that it's kind of out of order in the textbook, that's why. So ionic bonds are bonds between two ions, and I know that's a circular definition, but an ion is any charged atom. So atoms can be either positively charged or negatively charged, depending on if they have an extra electron or if they have lost an electron. If an atom has lost an electron, it's going to have a positive charge because it will have more protons than it has electrons. If it's a negatively charged atom, it's going to have more electrons than it has protons. Okay. The poster child example people always use for an ionic bond is sodium joining to chlorine to form salt. Sodium is an atom that has, I believe, 11 protons. It has 12 neutrons. And if it has 11 positive charges in its form when it is neutral, it would have 11 electrons. So 2 in the first shell, 8 in the second shell, and that gets me up to 10. And then in the third energy shell, it would have 1 lonely electron out there. The further away an electron is from the positive charges of the proton, the more likely it is that it may or may not stay attached to this particular atom. Chlorine, by contrast, has, I believe it has 17 positive charges and 18 neutrons. So it has an atomic mass of 35. And again, then we would put 2 electrons in the first shell, 8 in the second shell, and then in that third shell, there would be 7. 2 plus 8 would be 10, and I have 17 electrons. So 1, 2, 3, 4, 5, 6, 7. Again, those of you that have had a little bit of chemistry, you know that atoms prefer to have their valence shell or their outer shell full. So in this case, chlorine would like to have 1 more electron out there. And since sodium only has 1 electron, it's very likely it's going to give that electron away. An ionic bond is formed between 2 ions. As soon as this electron leaves sodium and goes to chlorine, chlorine is going to become an ion with a negative charge, and sodium is going to become an ion with a positive charge because this one lost an electron, this one gained an electron. And now they're going to form a bond because of this electrical attraction of a positive charge and a negative charge, and they're going to form this molecule, sodium chloride. Okay. So in an ionic bond, electrons are actually transferred from one atom to another. When this happens in multiple times, this sodium and chlorine can form a crystal, and you've of course seen table salt, and you can look at the picture that's in your book, right? A covalent bond is very different. So this is an ionic bond, example of an ionic bond, right, between 2 ions. Covalent bonds are very different because covalent bonds, no electron is leaving completely one atom and moving to another one. The electrons are going to be sharing. Okay. Depending on if the sharing is even sharing or unequal sharing, gives us non-polar covalent bonds or polar covalent bonds. So I'm going to draw a picture probably of water because it's a polar covalent bond, and maybe we'll do methane because that's a example of a non-polar covalent bond. You can see pictures of those. The non-polar covalent of methane is figure 210, and the polar covalent picture of water is going to be figure 211. These are really important, both of these, particularly the water, because we have a whole chapter 3 about water, which we won't have time for today, but we'll talk about tomorrow. And it's all the properties of water are based on that polar covalent bond. So I'll erase again. So in a covalent bond, electrons are not given away, but they are shared. And as I mentioned, a non-polar covalent bond example would be methane, which is CH4, and it was carbon, and carbon has an atomic number of 6, so there's 2 electrons in that first shell and 4 in the second shell. So it has almost this perfect storm. It has 4 electrons, it would like 4 more. It only has 6 plus charges in the center, so it can't attract and keep and steal 4. So it's like, oh, maybe I can share with someone. Maybe I can share with 4 people. And in the case of methane, it's going to share with 4 hydrogen atoms. Each hydrogen atom has 1 positive charge and 1 electron. So hydrogen's very happy sharing with carbon because it would like to have 2 electrons, right? It doesn't have enough positive charge to steal an electron from someone, but it'll frequently share. This is non-polar because the sharing is equal, and what we mean by that is the electrons spend equal amounts of time around the hydrogen protons and around the carbon protons. Even Steven, non-polar. Polar indicates that there is a charge or an orientation to a particular molecule, and the poster child for that is always water. So we have oxygen with our 8 protons in the center and 8 neutrons. And it has 2 electrons in the first shell and 6 in the second shell. 1, 2, 3, 4. They are often in pairs, but I'm going to split this last pair because water, H2O, is going to share with 2, oxygen is going to share with 2 hydrogen atoms. You put a smaller molecule here, a smaller hydrogen, and another smaller hydrogen here. Okay. Polar, because hydrogen's so small, he only gets the electrons part of the time. So because of that, there's a slight positive charge on these hydrogens and a slight negative charge here on the top of this oxygen molecule because the polar, the orientation, because there's a charge difference because the oxygen is so much bigger. Think of it like a sibling that's an older brother or an older sister who gets the toy most of the time, right? There's 2 kids, and they're the same, and they both want the truck, right? The older child usually gets the truck most of the time. Think of it like that. They're getting the electron most of the time, right? Hydrogen occasionally is like, hey, can I have my electron for like 5 minutes? And the electron zooms around the hydrogen, and then it goes back to spend more of its time around oxygen, which is why we get this little positive charge here, because the hydrogens have that 1 proton. Now, only in polar covalent molecules, this is going to set up a situation where this hydrogen can form a second bond to another polar molecule. And that situation is called a hydrogen bond, and they are very weak compared to these other types of bonds that we've discussed. And we draw them as a dotted line, not as a solid line. And space here, each water molecule can form 4 hydrogen bonds with other water molecules. So this negative polar end of the oxygen of hydrogen of water molecule number 1 is attracted to this hydrogen as well, or I should say this hydrogen is attracted to this oxygen. So I would get 4 of these. And down here, I don't have space, but down here, the big oxygen would be pointing, right? Hydrogen, hydrogen. The big oxygen would be pointing its negative charge toward this particular hydrogen. This is the hydrogen bond. And we describe it as a hydrogen atom that is covalently bound to, usually it's an oxygen or nitrogen, but also attracted to another nitrogen or oxygen. And again, these hydrogen bonds are weak, which is why we draw them as dotted lines. You can break individual hydrogen bonds. They only last for like a millisecond. They're frequently broken and remade over and over again. Individually, super weak. When you have hundreds of them, super strong. And the last little bit just gives you some terminology for chemical reactions. I think they show you some chemistry, like some pharmaceutical drug chemistry there with receptors for particular molecules. It's great to read. I'm not going to ask you specific questions about it. I don't think I included them in specific questions about those molecules. But concept 2.4 about the terms of a reactant, a product, reactions being reversible, those are important to just at least look through before that sort of the end of the chapter.